One of the consequences of Snell's law is that if we have a ray going from a higher index of refraction to a lower index of refraction, there becomes the possibility that the incident angle is so large that the refracted ray becomes 90 degrees. And what that means is that the light from the higher index material can't escape. Because once we go beyond 90 degrees, essentially the light isn't leaving the higher index material. Let's take a look and see how that happens. And again, this is according to Snell's law. So we see the first case, and again, we're going from the bottom to the top here. We see the first case, the angle of incidence is equal to 0. So basically, by Snell's law, the angle of refraction also has to be 0. However, now we're going to increase the angle of incidence. And again, I'll draw normal lines just so we can see this a little bit better. Here's a normal line right here. And we can clearly see, here's our angle of incidence, here's our angle of refraction. And the angle of refraction is greater than the angle of incidence. It's Snell's law. N1 in this case is greater than N2. Go to the next ray. Again, we're increasing. Now we're getting to fairly large angles. We're getting to large enough angles where the angle of refraction is beginning to approach 90 degrees. And again, if we make this angle even larger, we eventually get to this case, which we call the critical angle, where the critical angle represents the angle of incidence such that the angle of refraction becomes 90 degrees. And clearly, if my refracted ray is traveling at 90 degrees, it's not leaving the higher index material. It's going to remain trapped there. And really, this is talking about a ray that can't carry any energy out of the material. So where does the energy have to go? Well, basically, all the energy has to remain in the reflected beam because, again, you have two basic beams that we get when we reach an interface like this. We have the reflected beam, which, as the angle gets greater and greater, is actually getting brighter and brighter. And then finally, we reach this 90 degrees, where essentially 100% of the total energy that reaches this interface, 100% of the incident ray, is now going to be reflected. And that's what we call it total being 100%, total internal reflection, internal, it stays within the higher index material. And this is a very, very powerful phenomena to create certain devices. And again, the critical angle isn't just the angle where we're going to get 100% reflection. Anything greater than the critical angle is also going to be 100% reflected. So let's say our critical angle is 45 degrees for the incident ray. An incident ray of 50 degrees, 60 degrees, they're all going to be totally internally reflected. Now, how do we calculate the critical angle? What we're really doing is we're setting, with Snell's law, we're setting the sine of the refracted ray to 90 degrees. Or I should say the angle is 90 degrees. We take the sine of 90 degrees. That's going to give us 1. So again, just to remind you of Snell's law, we know that Snell's law says N1, okay, in this case, this is the index of refraction of the incident beam times sine of theta. Here we're going to solve for theta such that it's the critical angle, okay? This is equal to N2. N2 is the index of refraction of the lower index material. Usually this is air, it can be other material. And then, of course, we say sine of the refracted beam, but we've already said this refracted beam is going to be equal to 90 degrees. The sine of 90 degrees, of course, is equal to 1. Okay, so the sine of the refracted beam just simply disappears. We now solve for the critical angle, or the sine of the critical angle becomes n2 divided by n1. N1 we divide from both sides. And then if we want to solve for the critical angle, we have to take the inverse sine, the arc sine, again, of n2. N2 is the lower index material, N1 is the higher index material. And this is really key here, because if we look at this, if we look at what's going on here, if N2 is greater than N1, we get a number greater than 1, and you can't take the arc sine. You can't take the inverse sine of a number greater than 1. You're not going to get a physical angle. So the only way that this works is for the case where our material, which we're entering or trying to enter, is a lower index of refraction. The material that we're trying to leave is a higher index material, okay? So again, N2 is lower than N1, and therefore we can get a critical angle. So total internal reflection only happens as we're approaching an interface where the index of refraction is dropping. And again, the critical angle just goes by the arc sine of N2 divided by N1. Again, what are the applications for this? Well, there are actually quite a few applications. The first thing that you can do is essentially with 100% reflection, you've trapped the light in the higher index material, but you've also reflected the light at 100%. So for instance, if I want to have some optical system where I don't lose any of the reflected beam, okay? Yeah, it says here 80% reflection for metallic mirrors. A good metallic mirror is going to be about 95%. But if I want that 100%, because with every reflection, I can lose energy. For instance, in the case of prism pairs, we can use total internal reflection to basically not lose any of our light. Now, prism pairs are found in binoculars. And the reason why they're used is we know that with every reflection, we get some right to left reversal. But one of the problems that we'll see later on, when we're looking at telescopes, because a binocular is really two telescopes put together, is that the image becomes inverted. By taking a pair of prisms, we can invert the image again. We can put the image right side up. And that makes it easier for us to process what we're seeing as we're looking through there. If you're looking through a telescope, you might notice that if it doesn't have one of these prism pairs, that everything appears to be upside down, and it's a little bit more difficult for our brain to process what we're looking at. By inverting the image again after the telescope has inverted the image, we get an image that's right side up. And the prism pairs are superior to using two mirrors. Yes, I can accomplish the same thing if I had simply taken two mirrors at 45 degrees, one mirror here and one mirror here. But again, the problem is, even with the best mirrors, we're only getting 95% reflectance, which means after two reflections, I'm losing a fairly significant amount of the light. I'm degrading the image that I'm seeing. Whereas a prism, and we'll talk about also coating the prisms with anti-reflection coatings, we can get basically 100% of that light passing through in a really good optical system. And here you can see how the pair of prisms will work in a pair of binoculars. Again, you have the objective lens right here, okay? You have the eyepiece right here, and those intervening prisms are going to flip the image upside down because the telescope part itself is going to invert it. What happens at the interface is actually interesting. the limit that we have with the ray diagrams has already been discussed. The ray diagrams are good for giving us some information, but they don't give us all the information. What actually happens here is that as we have a ray approaching this interface, and again, going from high index to low index, and if we want to draw the rays, we can see that the rays would be perpendicular to these wavefronts. The blue and white represents peaks and valleys of the wave coming in. We can clearly see the incident beam coming in. I'm not showing the reflected beam. There would be, of course, a reflected beam going off in this direction, and the wavefronts would be going this way, which just complicated the picture. But what we see here is we see the incident wave heading this way, but we also have a refracted wave too, okay, even if we're beyond the critical angle. Now, first of all, we'll consider the case of a normally refracted beam or wave of light. Here's our incident beam. Here's a refracted beam. We're not beyond the critical angle, so some of the light is going to make it out. Some of the light is going to be reflected back in, okay? Here we can clearly see that this wave is going this way. Okay, when we reach the critical angle, what actually happens is some of the wave still makes it outside of the higher index material. And we can see this wave front right here. We can see the peaks here. Blue was probably not a great choice. Here's the minima, which are propagating here. And in actuality, what we have here is what's called an evanescent wave, which means that if I take my surface right here, that's also not a great choice. Let me go to red. It'll show things just a little bit better. Let's say my intensity as a function of distance going in the direction, in the x direction here, and the y-axis is going to represent the interface between high and low index material. So what happens is the incident ray comes in, and then we get this evanescent wave, which exponentially decays. It travels a few wavelengths at best, usually a fraction of the wavelength. This evanescent wave that barely makes it out, but because the pointing vector for this is pointing this way, energy cannot go from the higher index to the lower index material. Can't make it out there. So with total internal reflection, you do have some of the wave actually penetrating into the lower index material. It just can't transfer any energy. Now, this can actually be used for a rather interesting application, and that's the fingerprint scanner. When you put your thumb, or you put your finger on one of these scanners, what actually happens here is the light is sent, here you can see this red probably represents a red diode laser. The light is being sent at the critical angle, incident in the critical angle. So normally what would happen is 100% of this light would be completely reflected back. And if this was shown on some sort of detector, we would see basically 100% over the detector array, 100% of the light being returned. When you put your finger there, what it does is it makes contact with this evanescent wave and allows the energy to be absorbed by the surface of your skin. So what the scanner will now see is, instead of a completely bright screen, it will see wherever the ridges in your finger are making contact, those will appear to be dark, and that's very easy for the detector to read and then convert into an image that it can process and identify that in fact is your finger. So this is what we call frustrated. It's called frustrated because, again, we make contact with that evanescent wave, so we can transfer energy and it can be absorbed onto your skin, and that frustrates or overcomes the total internal reflection. The most important application, of course, for total internal reflection is actually the fiber optic. And this is showing technically what is really a light pipe. You can see the beam bouncing back and forth inside probably what's lucite. And because it's not high quality material, you can actually see the beam inside there. But every reflection is 100% reflective, and we can trap the light that way. Light pipes are used whenever you don't want to, you don't need to send high quality information. Light pipes are used in, a variety of different displays. I'm trying to think of, I should have put down, some pictures of it. Like certain Christmas displays will have like plastic, fibers coming out, and you can see the light being shown down the fibers. This is also used for just general illumination in small areas, and also for directing light into buildings. People use sort of these light guides to bring light into places that it's not convenient to have a window to bring natural light in. But the fiber optic is most important for sending data communication. And in our ray approximation, we really don't do it a lot of justice. A fiber optic is better understood as a waveguide, but we can understand it in terms of total internal reflection. With a fiber optic, we have a higher-nix core where the light is going to bounce back and forth inside the core. And again, if this fiber optic just had, a metallic reflector around it, it wouldn't take very many reflections before you've lost most of the energy from your signal. But again, in the ray approximation picture, we can understand that once the light enters the fiber optic, it's stuck in the core as it bounces off the cladding. Now, it's a better way of looking at this in terms of a wave, and this is the intensity of the wave as a function of the radius, a wave which is trapped by total internal reflection, where most of the energy is in the core and a small amount of energy, similar to the evanescent wave that we talked about before, propagates into what is known as the cladding, the lower index material. So again, ray approximation does give us somewhat of a picture of what's going on, but really the fiber optics are better understood as waveguides, where the size of the core is very, very small, and it only allows one mode of propagation there. And again, fiber optics are very, very effective because they can take this light energy at a very long distance. If you have ultra pure glass that you're using here, you don't really get very much absorption. But one thing I should remind you, something we talked about in the previous chapter, is that typically this is not sent in the visible part of the spectrum, even though the visible part of the spectrum would give you more bandwidth. For long distance, we either send it at about 1.3 microns or 1.5 microns. And that's still near infrared. We're still not far off. If you remember, I think 780 nanometers is typical for the red edge. So that represents 0.78 microns. We're not that far away from those wavelengths in the visible. Okay, so there's your application for total internal reflection. Again, it only occurs when we're going from a higher index material to a lower index material. You can actually see this effect if you're underwater in a pool and you look up, okay? You can see out of the water in the direction directly above you. But if you look at a steep enough angle, so let's say this is the surface of the water, and you are down here underwater. you can see basically everything above the water in sort of, this angle. But as soon as you start looking further down, the top of the water looking up looks like a mirror because you get that total internal reflection. Okay, that's it for total internal reflection. Again, it's all based on Snell's law.